Hi, in today's video we're going to be talking about alkene oxidation. And so let's look at a simple cyclic cyclohexene molecule. So one of our reagents for oxidation is called MCPBA, and we'll see what that means in the next slide. MCPBA reacts with an alkene to give you an epoxide, a three-membered ring. Another oxidation reagent for alkenes is osmium tetraoxide, and you often do that in the presence of a molecule called NMO, and we'll see why as well. This interestingly gives you a syn diol, so that is a diol, two alcohols that are both added on the same side or same face of the molecule. Notice that we have been able to open up epoxides in the past with either sodium hydroxide or under acidic conditions of an acid in the presence of water, and that gives us the antidiol, that is a diol where the two oxygen atoms are on opposite sides of the molecule. So now we have a way of making a syn diol as well. So the way the epoxidation mechanism works with MCPBA, we first have to look at the structure of MCPBA. Well, MCPBA is meta-chloro peroxybenzoic acid. So this circled portion is the peroxy acid, and this is kind of the business portion of the molecule. This is the reactive portion. The rest of it is in place in part because this molecule is relatively stable. Peroxy acids can sometimes be explosive, but MCPBA has been found to be a non-explosive variant that makes it really handy to use for organic chemists. So the way that this reaction works is that the alkene and the peroxybenzoic acid align themselves somewhat like this. The mechanism I'm about to show you is called Bartlett's butterfly mechanism. I'm not sure if you can see the butterfly in it, but if you do, we can talk about that. So one of the things I want to highlight in this is that this portion of the molecule is a good leaving group, and this oxygen-oxygen bond is actually quite weak. So this, I want you to remember back to the bromination reaction where there's Br-Br, where the bromine-bromine bond is weak and the bromide is a good leaving group. There's a similar type of mechanism where the alkene reacts with one of these atoms, and in this case the electrons kind of go all over the molecule, and eventually the molecule ends up attacking back or adding back electron density to make the extra bond between the carbon and the oxygen. And so if you follow all of these bonds, you'll see that this whole portion leaves along with this proton that is abstracted from this terminal oxygen atom. The transition state is interesting in that all of the bonds are being made and broken at the same time. And I tried to highlight and color code kind of the electrons that were in the original bonds and where the new bonds are being formed. So after this reaction, the side product that we often don't talk about is a carboxylic acid. So it's a relatively stable side product that is coming off of this reaction. Now let's look at the reaction where you form a syn diol. So you have osmium tetraoxide and you have an alkene. Now you notice that osmium has lots of bonds to oxygen here. And that's because osmium is a pretty large metal and is able to make lots of bonds. It has many orbitals at its disposal. This reaction undergoes what's called a cycloaddition reaction. So the alkene and these oxygen atoms, all these bonds are being formed and broken at the same time. And when you do this, you go from an osmium that has an oxidation state of 8+ to an osmium that has an oxidation of 6+. That means the osmium has been reduced and this carbon has been oxidized. And so now I've color-coded the oxygen atoms that came from the original osmium tetroxide. Now at this stage, there's water present, and water can hydrolyze away the osmium through a multi-step mechanism that we don't really need to discuss here. And this gives you now this osmium-6 species, where the oxygen atoms are now the oxygen atoms that came from water. The reason we throw in NMO is because osmium is relatively expensive and relatively toxic, and so we want to use a catalytic amount. NMO, N-morpholine, N-oxide, that's the name of NMO, this is the structure of NMO. This molecule acts to reoxidize the osmium-6 back to osmium-8, so it can be reused in this now as a catalyst. So you can use a catalytic amount of this toxic element. And it's often a wise idea to use a catalytic amount if you have a metal or an element that is toxic and or expensive. Well, thank you for your time, and I look forward to answering any questions that you may have.